In this submodule, I will explain extra details regarding application writing. We start by breaking up the command that sends instructions to the QMPU and explain the purpose of the future objects, some common pitfalls when using them, how to get if statements into the netchasm routines, and we will close by demonstrating some useful utility methods. Let us move on to netchasm's finer detail, specifically what happens in the connection.flush command. There are two things that happen in the connection.flush, namely first the subroutine is compiled. We can visualize this by first creating the subroutine via the connection compile command. We can then show you this subroutine by printing it. And lastly, we can then also show you that the current code is still functional, and it's actually the subroutine that gets executed by providing the subroutine to this connection and then .commit subroutine. So if I press Shift F10 and run the simulation, we see we still get the last bit of the print statement, so our simulation ran fine. But we also see this chunk of code over here. This is the netchasm language, specifically this last section. Over here you see quite a lot of commands. Most of these will actually be commands for the classical registry inside the classical controller architecture. But there are parts of this over here that are specifically coupled to the routine that we've just created. So for example, we can see the qubit initialization over here. Then we see the Hadamard gate over here, the CNOT over here, and then we can also see the measurements, etc. So there are some implications to how the measurement results interact with these with the sending the subroutine to the QMPU. That's because all of the simulation of these subroutines happens inside this line of code. Thus that means that before this line of code, this set of instructions have not happened yet. In order to deal with this, there are also some special objects, definitely for the measurement results. They are called futures, and they act like integers when they have a value, but when they do not have a value yet, they do not act like them. So if we try to print the measurement results before we send the instructions to the QMPU, we get this error. That's fairly reasonable because these simulations and also these measurements have not happened yet, so we cannot show the measurement results. But if you run it after here, it runs just fine. But there are some more implications to these M1 and M2 being these future type objects. Namely, there are some operations that do not function as expected. So for example, if we try to compute the multiplication of M1 and M2, we see that again we get an error. So we have to first convert these measurement results into integers. So now the code ran just fine. So in general, it is best practice to convert these measurement results to integers as soon as you leave the scope of your quantum program subroutine. There is another issue we face with the measurement results being future type objects and not occurring after we do the until we do the connection.flush. Namely, suppose that we want to condition our code on our measurement result. So suppose we want to apply an X-gate to the second qubit before we measure it, depending on the value of the first measurement. So Suppose we want to do something like this, Q2, and I'll apply an X-gate to Q2. Well, if we now run this code, we see we again get an error. That's because these instructions, have not happened at this moment yet. We need to first send them to the QMPU before we have an M1 value. So there are two ways to deal with this. The first one would be to, for example, place the connection.flush before the if statement. So we can run it and we see it runs fine. So this works in simulation. There has now no downsides in the simulation. But if you would run on real hardware, there is actually a cost to first compiling the instructions and then sending them to the QMPU. In this time period, the qubit can be decohering while you're doing this. So there is actually a better way of doing this, and that is to use some inbuilt Netcasm SDK methods. And those are located on the future type objects. So the M1 has a if equal method, and then we can create a conditional statement. And we say that M1 has to be equal to 1. And then if we run this code again, we see that it now runs fine. And if we run it a few more times, we see that if M1 is actually 1, it will, X-gate will be applied to M2, resulting in this behavior.